Thank you, Dr. Matthias, for the opening monologue. You've already said everything I have written down for this second part. I know that you have a lot of questions already, all of the guests here, but please wait for the questions and answer session for your questions. Now, as Dr. Matthias already said, please welcome a key member of the design and engineering team, Dr. Maximilian Maigler, a German aerospace engineer specialized in hypersonic vehicle design and computational simulations. Dr. Maigler is the person who ensures that the samples and onboard electronics after 9 months in orbit survive the atmospheric re-entry. Dr. Maigler, the stage is yours.
Yeah, thank you everyone. My name is Max. I'm as you mentioned, a German aerospace engineer. Did my PhD in Munich, and I'm now head of flight physics at a hypersonic startup. And within the Gen capsule program, I was responsible and hired for laying out the reentry system, essentially all the structural components that hold together the internal components, and that must protect the internal components during reentry. So basically, this is called an aeroshell of reentry vehicles, so RVs. Everything that surrounds the internal components, so the thermal protection system, the back shell, and the base plate or isolator that insulates thermally the high temperatures that you see during reentry. Then I will quickly lay out the methodology that I use to simulate and to design the capsules out of shell. And then finally, how they actually look like in CAD and some results from the simulations. So first of all, the aeroshell is by definition the primary protection system during reentry. And during reentry, because the velocity is so high, the temperature around the capsule gets so hot that you see plasma, dissociation of the air, and high pressure. And that affects the capsule, especially the thermal protection system, and has to be addressed by certain materials, thicknesses, and shapes. Because the whole goal of the reentry itself is to decelerate the vehicle from hypervelocity speed, so we're talking more than Mach 25 up to Mach 30, to subsonic velocity, where you can actually deploy your parachute, which is then used to decelerate the vehicle further so it can land on Earth. And what we're basically interested in is this pretty simple equation. So when we design those aeroshells, especially the thermal protection system, is that the convective heat flux that comes from the air onto the surface of the capsule must equal in equilibrium the radiative heat flux. And radiative heat flux is essentially when you see a metal, for example, glowing, it radiates heat away, and this is actually proportional to the 4th power. So there will be an equilibrium temperature based on the wall temperature and the background temperature of the fluid. And so usually why those aeroshells are black is because in this equation, you can't see my mouse, but this epsilon here, that's the emissivity. So you like to have something that is as close as possible to a black body radiator. And you like to have a small background temperature. So your temperature difference is high and your equilibrium temperature is lower. And this is basically the whole equation that is used to make the simulation in terms of the ball boundary condition, to estimate the temperatures in 3D on the surface, from where you can derive your materials, your thicknesses, etc. So this is an example of the space shuttle. You see all those black tiles here, again, to increase the emissivity of the material. Here you can see another image from the Apollo capsule after re-entry, and you see that ablation occurs, and this is actually where material is removed because the heat is higher than the melting temperature, that some energy is actually lost by removing material from the surface. And this is actually to some degree wanted, because then you also decrease your equilibrium temperature. So this is called an ablative heat shield essentially. But if you want to be reusable multiple times, you have to minimize that ablation rate. And this is also something I try to consider when designing the TPS system. So to quickly show you the methodology of how to do those simulations and which methodologies are used. It's basically that you first start with an analytical model. There's lots of data available from the literature when it comes to reentry. There were lots of experiments in the 50s and 60s by the Americans, but also publicly available data that you can use to make an analytical model with essentially a 0D model with Python or C++. And from there, you make a rough estimate of how your reentry is going to look like. And based on that, you can then continue with high fidelity, like CFD or DSMC, so computational fluid dynamics or direct simulation Monte Carlo methods in order to precisely determine the aerodynamic coefficients, which determine by themselves the trajectory that the vehicle is going to take during reentry. Because actually the trajectory itself has a high impact on how the heat loads are going to be distributed during time. And after this trajectory analysis, you can start to make a optimization of the heel sheet, so the thickness, the material type, and the shape. And finally, what you then have to do is, when you have the outside surface shape and material, make a conductive simulation to simulate how the heat is internally distributed during the reentry, in order to decide on wall thicknesses, materials, also where the PCBs, which are really temperature sensitive, are going to be mounted. And ideally, you would like to have something with an extremely low thermal conductivity, and for the thermal insulation, and something with really high thermal conductivity at the TPS. So this is how a analytical simulation looks like. This is a code I wrote, which essentially tracks the position and velocity for a re-entry case. So you start at 150 kilometers, as you can see on the left side. And you can see that the actual re-entry takes only place the last 10 minutes. You can see here on the bottom the curvature of the Earth in gray. And the last 15 to 20 minutes is only the actual re-entry. The path before that, so from 150 kilometers, there's no clearly fixed altitude where you say that you start re-entry, because that is determined by the local atmospheric properties, which are determined by the sun's activity, for example. But it's important to have a very precise atmospheric model in order to predict how the re-entry is going to look like, the trajectory itself. And from there, you get the boundary conditions, which you then have to employ in your high fidelity simulations in order to see, like, at which altitude, which free stream density, free stream temperature do you get which heat flux. So this is a close-up of the re-entry, and you can see that the re-entry from 150 kilometers here versus time starts for about 5 minutes, and then at an altitude of around 60 to 80 kilometers, this is usually also for the space shuttle and 90% of the re-entry vehicles the most harshest region, because there the speed is the highest and the Mach number is the highest, combined with already an atmosphere that is quite dense, and that is why most of the deceleration takes actually place between 60 and 80 kilometers of altitude. You also notice that in that region, you have a minor decrease in altitude, and this is because you orient the vehicle in a way that it is not normally aligned to the free stream flow, or parallelly, if you will, but you have a slight angle of attack. This is called a lifting re-entry approach. And this is important to have not a too steep angle in re-entry to minimize your heat loads on the system, because it's a compromise between the time that you spend on those atmospheric levels, and also the velocity that you have instantaneously. In those plots, you can see four graphs. On the top left, we have the wall heat flux in watts per meter squared. If you multiply that with the surface area, you get the actual power input into the capsule over time. On the right side, we have the local Mach number. It actually starts at Mach 15, the re-entry, and this is because the local temperature of the atmosphere in very high atmosphere altitude is around 1000 Kelvin, so the local speed of sound is actually much faster. But as you decrease your altitude around 60 to 80 kilometers, your free stream temperature is around 200 Kelvin, and that's where you experience the highest Mach number. And the actual stagnation point heating, so the point with the highest heat flux, is occurring actually at the highest Mach number, because there's a quadratic relationship between the heat flux and the Mach number. And for SiC on the bottom left plot, the red curve, you see how it heats up from 300 Kelvin to 2000 Kelvin. And there you see a little bit of ablation, which is reflected on the right plot, where you see 0.8 millimeters of recession actually from the thermal protection system. And that basically is the input that you need in order to make the CAD model and to narrow down essentially the thickness and shape of the capsule's TPS system. So what I will show you now is the simulations, the high fidelity simulations. So I mostly relied on DSMC simulations because the characteristic length of the capsule is pretty small. So the DSMC method is essentially a particle-based method which is used for rarefied and near continuum flows. And it's pretty easy to also run chemistry, because during the reentry you see temperatures in front of the vehicle up to 20,000 Kelvin actually, which produces those plasma conditions and also the dissociated air like atomic oxygen, atomic nitrogen, electrons, etc. And I used a starting altitude of 200 kilometers at the rarefied flow regime. There's a quantity which is called the 𝗚𝗃 number, which is much greater than 1, so we have to use the DSMC method for that. And the final altitude, where the heat flux then reduces rapidly, is carried out at 50 kilometers, where you still have some thermal, chemical, and thermal non-equilibrium flows. And these high-fidelity simulations are also used then to validate your analytical model, essentially. So what you can see here is the third version of the GEN capsule, and this is in the volume rendering the temperature around the capsule at 200 kilometers altitude, and this is 1.2 E4, so we're talking about 12,000 Kelvin of actual temperature around the capsule. But in that altitude, the density is still very low, so the actual heat flux onto the capsule has not peaked yet. And this is how it looks like if you have a lower Earth reentry, so lower altitude. So this is 120 kilometers, where the free stream temperature, the maximum temperature is 8,200 Kelvin, which you can see in the bottom left. And the total heat flux is shortly before peaking. So on the capsule itself, you see the heat flux, and on the free stream rendering, you see the temperature. And this is how it looks like, since it's a transient simulation, that you have pretty much steady state conditions. And what you then do is you have 1 second that you simulate, and then you take an average of this 1 second period that you've simulated in order to derive steady state quantities for that altitude and velocity, and to validate also your analytical model. This is now going lower. We are now at 60 kilometers altitude. So still in the highest temperature, you see 8,000 Kelvin in the fluid in front of the vehicle. It's called the stagnation zone. And this is actually, as you've seen in the previous plots, the harshest conditions actually. So you have already a high density of the atmosphere, but still, and also 8,000 Kelvin of temperature. So the heat flux is there because it's the convective heat flux onto the surface, which is determined by the density and the temperature, is then peaking in that point. I also made a rendering of the same case. So you can see the stagnation region in front of the vehicle, and also some recompression shock, we call it, in supersonic flow, is where behind the capsule you also have a recompression zone. And this is also the reason why you have a communication blackout, because those electrons and ions which build up the plasma during reentry, they in the boundary layer then flow around the vehicle and then hit the recompression shock, so you cannot communicate directly behind your vehicle. And then on the top left here, you can see the plot that I've showed you previously, the wall heat flux. If you would zoom in into that picture, you would see that the analytical model has matched like within 5% compared to the high fidelity DSMC case. And that is an excellent way of proving that what you essentially simulate with a high fidelity approach, where you can only have a few snapshots along your trajectory, is then fed into the comparison with an analytical model, and it matched nearly perfectly. So that gives a high confidence that those are the actual temperatures that are occurring, which you are precisely needing to, design your TPS. Yeah, and this is another section cut where you can see on both sides how the base plate is mounted onto the titanium back shell, and then those 6 holes are going to be the holes where you will mount the rods that hold the PCBs. And yeah, that concludes my presentation. Maybe as a final note, you can also see on the ring outside, it was a requirement by 𝗏𝗏𝗺𝗁 to have like a bolted assembly. And yeah, happy to take your questions afterwards.